Yes, in the last lecture we are discussing about uh, how to find the arc length of a curve. We will see that not in all the cases we can compute the arc length of the curve, but for certain a large section of the curve class of the curve we can find the arc length. So, let us take an intuitive idea about how to proceed. As we have seen, we had given a curve which is from A to B, and then we take the partition of equal length interval, and then what we do is that we join the two endpoints. This is x naught, f of x naught, and x 1, f of x 1. So, we join the straight line and then we go on like this. So, basically now what we had observed, if we are making our partition smaller and smaller, that is a natural definition for the arc length of the curve. So, now let us see what is the distance between we want to the length of the straight line which joins length of the line joining x naught f of x naught. Rather, we can say that f x I minus of 1 f of x I minus of 1 and x I f of x I. So, we know precisely what is the distance, what is the length of this straight line. So, the length of the straight line is equal to square root of x I minus of x I minus of 1 square plus f of x I minus of f of x I minus of 1 square. That is what is the length of the straight line. Okay. So, now let us assume that our function f is a nice function in the sense that it is differentiable and it satisfies the mean value property. So, then observe f of x I minus of f of x I minus of 1 divided by x I minus of x I minus of 1. This is equal to some f prime of x I star, where x I star belongs to x I minus of 1 and x I by mean value theorem for nice f. Right, that means the curve what we are looking at is a differentiable function to start with. So, then we can get this. So, this we can write this is the square root of let us denote delta of x is equal to x I minus of x I minus of 1. Then this is delta of x square plus f of x I star square, and then this is delta of x square. Now, if we take this out, then this is going to be square root of 1 plus f prime x I star square times delta x. Now, if we take our partition smaller and smaller, then and if we are given that this is f is is nice such that f prime is continuous, so on and so forth. So, this is an integrable function. So, taking the partition small, what we are going to get that this converges to a to b square root of 1 plus f prime of x square dx. So, that is what is going to be the arc length of the curve. So, let us so this L what we are writing is a to b square root of 1 plus f prime of x square dx. This is the arc length of the curve. So, which means you are looking for the curve which has nice property such that curve y equal to f x, which has nice property such that f prime is also continuous, then this has no issue in finding the arc length. So, let us do an easy example. Find the length of the curve. Y is equal to 1 plus 6 x to the power 3 upon 2 and 0 is lesser equal to x is lesser equal to 1. Now, what is our f of x? So, f of x is equal to 1 plus 6 x to the power 3 by 2. Therefore, f prime or dy by dx. So, if I calculate dy by dx, then this is going to be 6 into 3 by 2 into square root of x. So, now, so arc length is equal to, now the interval is from 0 to 1 and then this is square root of 1 plus this is 2 to 9 is 81 x dx. Now, of course, by using substitution we know how to compute this. So, this is probably going to give me 1 by 81, then this is 1 to square root of 82. No, t is okay. So, I will put it as 82 square root of t dt. So, this we can easily compute what it is going to be. So, similarly, I mean you can find the curve whenever the curve is given in the equation y equal to f x, you calculate f prime and look at the interval in which you are trying to measure the length of the curve, and that is going to be essentially through the integration. This is a very nice application of the integral. So, here what we are saying that our curve is given by y equal to f x, which means it is a graph of a function and this function is nice. Sometimes it happens that suppose you consider a particle is moving like this in this fashion. So, obviously, this we will not be able to represent it as y equal to f x, because this is going to break the rule of straight line. So, vertical line test, this is going to fail. So, this may not be, cannot, rather in this example cannot be written as y equal to f x. then how we are going to an estimate or calculate the length of this curve. Now, this for example, this what we are giving here, we are saying that a particle is moving like this fashion. Now, this particle is moving in this fashion means this what we are observing, that it is dependent on time, given a particular time where the particle is, that is how we are going to estimate. Just imagine that if you were traveling on on hills. So, you are going rotating and getting some height with the curve and all, but with the time you are moving the distance and traveling more and more distance given time. So, now how we are going to compute uh, uh, that. So, now it is we are going to represent this, suppose this point at a particular time t. Now, this is in the coordinate plane, this is x comma y. Now, this position x comma y, they are also function of time. So, x and y coordinate of the particle is a function, r function of time, that is x is equal to f of t and y is equal to g of t. And in the time interval you are looking at from A to B, let us say from 1 hour to 2 hour or something like that, whatever, but this is on the interval A to B. So, this is given by parametric equation. That means, there is a function f is a function from a b to r, and g is also a function from a b to r. So, all these x and y, they are been given in terms of a parameter in this particular example, that is the parameter is the time and which is on a fixed interval a b. So, such curves in general are called parametric curves. So, any curve given, any curve C given by is called a parametric curve. Okay. So, for example, the simplest example what we can take, let us take x equal to cos t and y is equal to sin t. Then what is going to be the shape of this curve? Now, the shape of this curve, as we know, if I look at the interval between 0 to t is less than or equal to pi, if I want to look at, then this is going to be a semicircle, or if I make it 2 pi, then this is going to be the full circle. So, now we would like to get the arc length of this parametric curves. Now, for the time being, let us assume that let us see some of the curve parametric which is given by the parametric equation can also be, by eliminating the parameter, one can get that y is some function of f. In some cases, by eliminating parameter t, we get y is equal to some f of x. So, as you can see that for simplistic, because this is what x is equal to f t is given, y is equal to g of t is given. Now, suppose our f is so nice, let us say the inverse exists. Okay. Then in this case, if inverse exists, then t can we can write it as f inverse of x. Now, this y I can write g of t, t is f inverse. So, here in this case we are getting that g is equal to capital F, some other, it is a function of f. So, in particular you know that if f prime is not equal to 0, then you can show that this is 1 1, and if f prime is also a continuous function, you can show that that is going to be f inverse is going to exist, and so you can do. So, some condition on this f can always give you land us into this situation where we can write y equal to f of x. So, let us try to see that if we have in this situation, what we are going to get as the arc length of this curve. Okay. So, now this what we are writing. So, this is y is g of t, this is equal to f and x is f of t. So, this is f composed of t. So, if I take the derivative with respect to t, then this is dy by dt is g prime of t, this is f prime of f of t into small f prime of t. Okay. So, this implies capital F prime of x, this is equal to g prime of t by f prime of t, if f prime of t is not equal to 0. So, in our notation, what is this capital F? This is dy by dx, this is equal to g prime of t, y equal to g t. So, this is dy by dt divided by dx by dt, provided if dx by dt is not equal to 0. This is what we are getting, that this is the, if we can write y in the form of x, then dy by dx is equal to f dy by dt divided by dx by dt. Now, the slope of the tangent of the curve y equal to f of x, then slope of c in this particular, where y is written as y equal to f of x at x f of x is f prime of x, right. So, now we can find the slope of the tangent at the curve. Now, for example, a curve C is defined by the parametric equation rather, y is equal to t q minus of 3t. So, now this is find the tangent at 3 0. Now 3 0 means I need to find what are the thing. This is the point 3 0. So, therefore, t into t square minus of 3, this is equal to 0. This implies that t equal to 0 or t equal to plus or minus of root 3, right. So, now if t is equal to 0, x is equal to 0, that, but we are interested in 3 0. So, t is equal to plus or minus of root 3. Now, we want to find the slope, that is dy by dx, which is nothing but dy by dt divided by dx by dt. So, this we can just compute it. In this case, this is at t equal to square root of 3, then what we are going to get is that, and dy by dx, if we look at 3 equal to minus of square root of 3, this is going to be, if we calculate, this is what it is going to be. Okay. So, now let us answer in this situation, let us try to get what is going to be the arc length. So, suppose C is a parametric curve, x is equal to f of t, y is equal to g of t, and alpha is lesser equal to t is lesser equal to beta. T, that means t increases alpha to beta and denote f of alpha, this is equal to a, and f of beta, this is equal to b. Therefore, in this case, what is your L, what we want to write? This is, we are trying to write a to b square root of 1 plus dy by dx whole square, right, dx. Now, this is equal to a to b. Now, if I change the parameter to t, making the substitution, then what do we get? We get dy by dx equal to dy by dt square divided by dx by dt square. Now, dx is what? Dx by dt x prime by substitution rule, and then this is dt. Now, this is a, because we are putting a to b is going to be, t will vary from alpha to beta. So, this if we compute, then this is going to be alpha to beta square root of dx by dt square plus dy by dt square, then this is dt. So, this is what if C is expressed in terms of the capital F. Even in the case if C is not expressed by the form of y equal to capital F of x, by polynomial approximation we can get this formula. So, let me write it down, the statement. So, this is the theorem. If a curve C is described by parametric equation x equal to f t, y equal to g of t, alpha lesser equal to t lesser equal to beta, where f prime and g prime are continuous and C traverse exactly once at t increases from alpha to beta, then the length of is L is equal to integral a to b Okay. So, this is irrespective of whether y equal to capital F of x, we are able to eliminate t or not. This is what is the statement. So, let us do some concrete example. Let us say simple what we have started with cos t y equal to sin t and then t belongs to 0 to pi. Then L is equal to dx by dt, dx by dt square is equal to 0 to 2 pi square root of sin cos t is minus sin t. So, this is square is sin square t plus dy by dt is cos t, square is cos square t dt, which is equal to 2 pi. That is what the length of the curve what we know. Now, another quick example. So, let x is equal to r t minus of sin t and y is equal to r 1 minus of cos t, and then again the interval is from 0 to 2 pi. So, you can compute the dx by dt square plus dy by dt square. If we compute that by taking the derivative, what you are going to get easily, you can see that 4 square sin square t by 2. So, therefore, the L what you are going to get is nothing but 0 to 2 pi. This is equal to square root is 2 r sin t by 2 dt, and which if now sin t by 2 we know the antiderivative, we can compute. So, you are going to get H r. So, this is even if we do not have kind of y equal to f x as a graph of a function, but any curve which is given by the parametric representation, that means x equal to f t, y equal to g t, then basically the length is going to be arc length is a to b square root of f prime t square plus g prime t square dt. That is what is going to be the arc length of the parametric curve. Okay, so, then in the next lecture what we are going to see is that sometimes the curve can be given by something called a polar coordinate. So, how we are going to do analysis, compute the arc length, the area if our curve is given by polar coordinate. Thank you.